These are some of the ingredients for manned spaceflight. A rocket launch vehicle with a combined power of more than 6 jet airliners, a spacecraft, and a man functioning as a vital, indispensable part of the entire system. Other ingredients are also necessary for manned spaceflight. A worldwide communications network to control and track the orbiting spacecraft. Also a task force of naval vessels and aircraft to recover the spacecraft as it returns to Earth. A single unified program brought these ingredients together and made spaceflight a reality. This is the story of that program, the program known simply as Project Mercury. Project Mercury was born October 7, 1958. Program approval was granted 1 week after the establishment of the new National Aeronautics and Space Agency. Program mission: put a man into space, orbit him around the Earth, and recover him safely. Program requirements: select a suitable launch vehicle, build a spacecraft, and train men to fly the space mission. The program began at once. A space task group was established to manage the program and direct the efforts of a team comprising the armed forces, other government agencies, and leaders of industry across the nation. Within 4 months, contracts had been let for the provision of launch vehicles and for the design and fabrication of a spacecraft. Selection of applicants for space flight training was also initiated. And so it began, a program of engineering and development almost unprecedented in its technical scope. For manned application, there could be no compromise of reliability. All components, each system and subsystem, must endure stresses and environments hitherto unexperienced. Aerodynamic heating, for instance, which can raise the temperature of a vehicle re-entering the atmosphere as high as 3,000 degrees Fahrenheit. There were problems in the early days of the program, but there were significant breakthroughs, too, such as the evolution of a special shape for the Mercury spacecraft. First the shape, then the size and weight of the spacecraft were determined. Large enough to contain all the necessary systems and a man, small enough to fit the airframe of the launch vehicle. The weight, well within the lifting capabilities of the vehicle selected to insert the spacecraft into orbit, Atlas. 67 feet tall, with a diameter of 10 feet. The Atlas is a 1.5-stage liquid propellant launch vehicle with 5 engines, 2 booster engines, a sustainer engine, and 2 small vernier engines. The total thrust produced by the Atlas vehicle, 360,000 pounds. The airframe skin, made from thin stainless steel, makes up the fuel and oxidizer tanks. 160,000 pounds of liquid oxygen and 73,000 pounds of kerosene-type fuel burn to provide thrust for 5 minutes of powered flight. Originally designed as an intercontinental ballistic missile, the Atlas needed structural modification to carry the Mercury spacecraft. Also, an adapter for the upper conical section. This work was undertaken together with a vigorous program of static testing. Also being tested was the Redstone rocket. This launch vehicle, developing 76,000 pounds of thrust, was selected to boost the spacecraft into a suborbital ballistic flight path and thus qualify all systems for later orbital flights. Like the Atlas, the Redstone vehicle was modified for manned application. A system was devised for both launch vehicles, which would automatically sense an incipient failure or critical condition and shut down the engine immediately. From the onset, pilot safety was the prime factor in Project Mercury. Every known contingency was examined. Every step was taken to safeguard the pilot from launch to recovery. Of major concern was an abort on the launch pad or during the boosted phase of flight prior to separation of the spacecraft. Against this contingency, an escape tower was designed for attachment to the spacecraft. A 17-foot pylon structure housing a powerful solid rocket motor with 3 nozzles. Triggered either by the launch vehicle abort sensing system or by the command of pilot or ground controller, the spacecraft is instantaneously detached and accelerated up and away from the launch vehicle. When a safe separation distance is reached, another rocket is fired to jettison the escape tower. The spacecraft's automatic parachute system then lowers it safely to Earth. To prove the escape system during flight, a special test launch vehicle was developed, Little Joe, a significant part of Project Mercury, designed, developed, and fabricated within 9 months of initial contract award. Built especially to test the Mercury spacecraft and its systems, the Little Joe's 8 solid propellant rocket motors could deliver a total of 340,000 pounds of thrust, capable of boosting the spacecraft up to 100 miles above the Earth. Little Joe was used to qualify the spacecraft for escape during critical conditions that could be encountered during an Atlas launch. It was also used to determine the effects of acceleration on a small primate, a rhesus monkey called Sam. The Mercury spacecraft, the heart of Project Mercury. 9 feet tall, 6 feet in diameter at the base, weight over 2 tons at launch. Its shape, design, construction, and function are for a single purpose: to carry a man into space, orbit him around the Earth, and return him safely. The metal used for the basic shell inner wall is titanium with a strength of steel at half its weight. Another high-grade metal, called Rene 41, is used for the outer surface shingles, which are corrugated for stiffness and then bolted to the spacecraft frame. The cylindrical end of the afterbody, covered with beryllium shingles, houses the spacecraft's parachute system. The dish-shaped heat shield, designed to withstand re-entry heat through ablation, consists of several layers of laminated fiberglass resin. The slow melting of this material acts to dissipate re-entry heat. Each development phase of the Mercury spacecraft and its systems was supported by exhaustive testing. The spacecraft had to withstand the combinations of acceleration, heat loads, and aerodynamic forces during launch, re-entry, landing, and recovery. Although a water landing was planned for all Mercury missions, provision had to be made for both water and ground impact. So a landing bag was devised by attaching the heat shield to the spacecraft with a rubberized fiberglass skirt. After the heat shield had done its job during re-entry, it is lowered and the skirt forms an air-filled cushion. Landing impact is absorbed by compression of the air inside the skirt. Test followed test under real and simulated conditions. As well as being small and light, the spacecraft had to be rugged. All of its systems had to be rugged also, rugged and reliable. Reliability had to extend to operation of the posigrade rockets, which separate the spacecraft from the launch vehicle. In the same package are the solid propellant retrograde rockets, which slow the spacecraft to permit re-entry and return to Earth. Their operation is equally critical. All rocket motors had dual ignition systems from separate electrical power sources to ensure the ultimate in man-rated reliability. Man-rated reliability, engineered into the spacecraft and encompassing all of its systems. Each fuse, relay, and connector in the 7 miles of wire which form the electrical system had to have this reliability. Concurrent with spacecraft development was that of major systems, such as the automatic stabilization and control system. The ASCS is essentially an autopilot which instantly senses deviations from the programmed flight attitudes. These are corrected by jets of steam and gaseous oxygen formed by the decomposition of hydrogen peroxide in the thrusters. The jets, released through these thrusters, provide impulses to correct the spacecraft's attitude in pitch, roll, and yaw. Although fully automatic, the pilot can select the fly-by-wire mode and manually control the spacecraft. This mode of control is selected by appropriate switches and effected by a specially developed hand controller. As the hardware was prepared for spaceflight, so too was the most important system, man. Early in the program, 7 applicants had been selected, each meeting the exacting physical and psychological criteria. Each a jet aircraft test pilot with a minimum of 1,500 flying hours, each with engineering background and training. And with their selection, a new household word was introduced, astronaut. These were the men who had become a vital part of the spacecraft system, and training for the space mission began at once. At first in the classroom to study celestial mechanics, astrophysics, and space medicine. They learned to survive in a variety of hostile environments, including the deserts and jungles of the Earth. They were also taught the techniques of sea survival, including the use of specially devised life-saving equipment. But survival in the space medium was the focal point of the entire training program, and the astronauts learned the physiological effects of space flight. Weightlessness, duplicated for less than a minute by flying an aircraft over a powered parabolic curved flight path, and the effects of rapid acceleration or deceleration, resulting in forces on a man's body equal to many times his own weight. Special devices were built to teach the astronauts the exacting skill of spacecraft attitude control in the conventional attitudes and the unconventional, as might be experienced in a tumbling spacecraft. The astronauts' activities were not confined to training alone. Working closely with design engineers, they made significant contributions to the development of the various systems. For example, the environmental control system and its pressure-tight suit, which cools the astronaut and provides him with breathing oxygen. In the event of spacecraft cabin pressure loss, the suit functions as an independent pressure envelope. Spacecraft interior layout and the positioning of controls and switches also benefited by the astronauts' contributions. Each regarded the Mercury spacecraft with a high degree of personal interest. One aspect of the spacecraft was uniquely personal, the astronaut's support couch. Each of the 7 had his own, molded especially for his body. The design of the contour couch was a feature exclusively developed by NASA for Project Mercury. Its shape enabled a man to withstand up to 20 Gs. Its construction of crushable honeycomb aluminum, bonded to a fiberglass shell and lined with foam rubber, had been well proved by a series of impact tests. A production Mercury spacecraft was ready for flight test with the Redstone launch vehicle some 2 years after program inception. This first launch attempt on November 21, 1960, comprised a strange admixture of failure and success. Slow-motion photography recorded the sequence of events which followed the start of MR-1's engine. As the Redstone lifted from the pad, the 2 tail plugs supplying ground electrical power failed to pull loose in the correct sequence. A resulting undesired voltage potential was sensed by the vehicle's abort sensing system, which told the engine to shut down. The Redstone then settled back onto the pad. Noting the shutdown, the spacecraft's electronic brain signaled for escape tower jettison. Sensing further that it was at a low altitude, the spacecraft then initiated deployment of its parachute landing system. Mercury Redstone number 1, a flight test failure, a successful demonstration of its system's capabilities. Less than a month after the first attempt, the same spacecraft was launched by vehicle MR-1A into a suborbital ballistic flight. All events occurred as programmed. The spacecraft attained a velocity of 4,909 miles per hour, was weightless for 5 minutes, and sustained deceleration of 11 Gs on re-entry. Recovery of the spacecraft after a total flight time of 15 minutes and 45 seconds was accomplished smoothly. On the morning of May 5, 1961, the primary goal of Project Mercury came sharply into focus. 3 successful unmanned flights had proved that the Redstone launch vehicle and spacecraft were ready for manned application. Today, the ballistic mission would be flown once again, but this one, Mercury Redstone number 3, would be different. For Navy Commander Alan B. Shepard, the countdown had begun months earlier. From the day he was selected to be the first American to attempt suborbital spaceflight, he had undergone 40 separate simulated flights. 3 days ago, he had stood as he stood now when the flight was scrubbed for weather. But today, May 5th, the weather was go. The launch vehicle and the spacecraft, named Freedom 7, were go. The launch pad crews and downrange recovery forces were go. As the launch and flight of Freedom 7 were monitored by Mercury Control, it became apparent that all systems were functioning perfectly. At 5 minutes and 14 seconds after launch, at a peak altitude of 116 statute miles, the retro rockets fired, and astronaut Shepard in Mercury spacecraft Freedom 7 began his long plunge back to Earth. Astronaut Alan Shepard, the first American to achieve spaceflight, was successfully recovered from Mercury spacecraft Freedom 7. His recovery, and also that of the spacecraft, completed all the mission objectives of Mercury Redstone number 3. The next step in the program was to confirm the mission's success. 2.5 months later, a Mercury spacecraft was once again prepared for flight. This one was slightly different, having an observation window for attitude reference and recognition of ground checkpoints. Another new feature was the explosive-operated exit hatch. The astronauts selected for the Mercury Redstone number 4 mission, Air Force Captain Virgil Grissom, entered the spacecraft at 3:58 a.m. on the morning of July 21st, 1961. 3 hours and 22 minutes later, MR4 was launched. Primary flight objectives were, as before, familiarize man with a brief but complete space flight experience, including the liftoff, powered, weightless, and landing phases of the flight. In addition, effectiveness of the spacecraft window was to be determined, and the explosively actuated hatch was to be flown for the first time in a manned spacecraft. Shortly after Liberty Bell 7 reached the water, the hatch blew prematurely. Astronaut Grissom escaped unhurt from the sinking spacecraft. However, the extra weight of water proved too much for the recovery helicopter to lift, and Liberty Bell 7 was lost. Despite this loss, the flight of MR4 was a success, having achieved all of its primary objectives. 2 manned suborbital missions had been accomplished. Project Mercury was now ready for the big one. The Mercury Atlas space vehicle, which was to put the first American into Earth orbit, had already undergone 5 unmanned flight tests, of which 2 had failed. 3 months ago, the 5th flight test, with a chimpanzee in the spacecraft, had successfully achieved 2 orbits of the Earth. The launch operation for Mercury Atlas number 6, which began in the pre-dawn of February 20th, 1962, was the largest and most significant to date in the Mercury program. At the launch complex, 2,600 people were engaged in pre-launch preparation. 16 tracking stations, forming a worldwide network, were manned by a further 1,100 people who were also making last-minute preparations. Spaced along the planned orbital paths were recovery forces, a task force of ships and planes in which some 15,000 personnel waited to play their part. And Marine Lieutenant Colonel John Glenn prepared for his role in this, the first orbital manned space mission, the primary objective of Project Mercury. For astronaut Glenn and the Mercury team, the test objectives for the MA6 mission of Friendship 7 were simple and clearly defined: to evaluate the performance of a manned spacecraft system in a 3-orbit mission and evaluate the effects of spaceflight on the astronaut. For those who watched and waited, an even more basic objective was recognized. Our nation was about to meet the challenge of manned spaceflight. The Atlas, with spacecraft Friendship 7, rose slowly at first, then much more rapidly as it gained speed with altitude. After 2 minutes, booster engine cutoff occurred as programmed, and the booster section was jettisoned. The escape tower, now unneeded, was also jettisoned. 5 minutes after launch, the space vehicle at an altitude of 100 miles, SECO, sustainer engine cutoff. The spacecraft was released from the launch vehicle and the posigrade rockets fired. As Friendship 7 was inserted into orbit, astronaut Glenn and his spacecraft became weightless. As the spacecraft orbited the Earth, it was passing from one tracking station to another. At a speed of 17,500 miles per hour, it takes only 88 minutes to circle the globe. Across the Atlantic Ocean to Africa, and then over the Indian Ocean into the night of Australia. Streaking into the sunrise, Friendship 7 passed over Hawaii and the Pacific Ocean. back toward its launch point in the United States. At the end of the first orbit, a thruster malfunction permitted only partial use of the automatic stabilization and control system. Astronaut Glenn took over and controlled the spacecraft manually. The second orbit over Mouchet, Australia, a ground telemetry signal indicated that the heat shield might be loose. A decision was made by Mercury Control to program re-entry with the retro-rocket package in place, and astronaut Glenn was instructed to manually override the automatic jettison mechanism.
Roger. Say again your instructions, please. Over. We are recommending that the retro package not, I say again, not be jettisoned. This means that you will have to override the 05G switch, which is expected to occur at 044353. This is approximately 4.5 minutes from now. This also means that you will have to retract the scope manually. Do you understand? Roger, understand.
Near the end of the third orbit, between Hawaii and the California coast, the retro-rockets facing forward were fired to slow the spacecraft for re-entry into the atmosphere.
Chute is out in reach condition at 10,800 feet and beautiful chute. Chute looks good.
Astronaut Glenn and his spacecraft Friendship 7 landed well within the planned recovery area. All mission objectives had been achieved, including a realization of the primary goal of the Mercury program, to put a man in orbit around the Earth and recover him safely. But the MA-6 flight had done even more. It had demonstrated conclusively that man was a necessary requirement for spaceflight to implement decisions beyond ground control limits, to supplement automated systems with his reason and technical skill. The scope of manned spaceflight had been enlarged. To further qualify the role of man in space and to demonstrate his ability to work in the new environment were now major goals of future Mercury flights. There were 3 more historic milestones in the Mercury program, represented by successive manned orbital spaceflights. All comprised the same basic operation, and yet each was different, contributing its own significant data to the overall program. Mercury Atlas number 7, Navy Lieutenant Commander Scott Carpenter, in spacecraft Aurora 7, accomplished 3 orbits for a total flight time of 4 hours, 53 minutes. The test verified the observations and results of the MA-6 flight and contributed valuable space science information. A combination of delayed retrofire and spacecraft alignment resulted in a landing 250 miles beyond the planned recovery area. Otherwise, the flight was completely successful. So successful, in fact, that a re-evaluation of the Mercury mission was made. This re-evaluation confirmed a previous decision to extend the number of orbits for future flights beyond the 3 originally planned. Mercury Atlas number 8, Navy Commander Walter Schirra, in spacecraft Sigma 7, accomplished 6 orbits of the Earth, 160,000 miles in 9 hours, 13 minutes. This extended mission, termed a textbook flight by astronaut Schirra, terminated when the spacecraft impacted less than 5 miles from the center of the recovery area. Most significant of the flight's results was the confirmation of engineering and operational techniques and procedures which had been developed for manned one-day mission. The last flight of the Mercury program took place on May 15, 1963, Mercury Atlas number 9. The spacecraft was named Faith 7 by its pilot, Air Force Major Gordon Cooper. Its mission, 22 orbits. Although the spacecraft was basically the same, it had been modified for the extended mission. It had an increased electrical power supply, also more man-required consumables such as oxygen and drinking water. In addition, certain system redundancies had been eliminated, thus making the astronaut an even more essential part of the overall spacecraft system. The flight plans for the MA-9 mission called for astronaut Cooper's participation in 11 different space experiments. These included specific aeromedical studies of man's reaction to extended orbital flight. Other experiments included weather observations, also space photography of dim light phenomena and horizon definition. Observation was also to be made of a specially devised flashing beacon, which was to be released during orbit. All programmed activities were accomplished. Astronaut Cooper demonstrated man's capability to eat and drink and sleep in a space environment. He also demonstrated much more. During the 19th orbit, a green .05 G light, similar to the one shown, illuminated prematurely, an indication of possible automatic control system failure. The remainder of the flight had to be made by using manual control. Astronaut Cooper was also required to manually fire the retro rockets and control the re-entry. After more than 34 hours in orbit, Faith 7 returned to Earth and was recovered successfully. The spacecraft landed within 8,700 yards of the prime recovery vessel. Project Mercury came to an unofficial end on that day in May 1963. In actual time, the program lasted 4 years, 8 months, and 5 days, during which time 900,000 miles were flown and a total of 54 hours of manned spaceflight time accrued. A nation intimately shared the successes of Project Mercury, and it also shared its failures. The names and faces of the astronauts, Shepard, Grissom, Glenn, Carpenter, Schirra, Cooper, and Slayton, were well known to the rest of the world. The names of their spacecraft, too, had become household words. To the nation, Project Mercury had a special significance, for it had proved that the closely knit team of industry and government could orient their efforts to the achievement of a common national goal. The ultimate success of Project Mercury, however, can never be fully told, for its story has neither beginning nor end. The program came into being as a continuation of man's effort to meet the space challenge, and is being carried on through more advanced programs such as Gemini and Apollo. These and future programs will share a common heritage to ensure their success. A heritage of science and engineering, design and technology, experience and knowledge. The sum of these is the spaceflight legacy bequeathed to all men by Project Mercury.